Welcome back to Basic Electronics. Earlier in this course, we have seen diode circuits for various functions such as peak detection, clipping, and clamping. We have seen that because of a finite turn-on voltage of the diode, the waveforms for these circuits are not quite ideal. We will now look at a combination of a diode and an op-amp for accurate peak detection. We will see how this circuit can be used for AM demodulation. So let us begin. We will now discuss how op-amps can be used for the purpose of rectification along with diodes. Let us start with a half-wave rectifier. Here is an ideal half-wave rectifier, black box. Input Vi, output Vo. We want the output voltage to be 0 if Vi is negative, and if Vi is positive, we want Vo to be equal to Vi. That's a straight line going through the origin with a slope of 1. These are the time domain waveforms, that is Vi, and Vo would be equal to Vi when Vi is positive, and Vo is 0 if Vi is negative. We have seen this diode circuit which was used for half-wave rectification, but this had this diode voltage drop V on here, and therefore the VO-Vi relationship is not quite what we want, and this can become an issue if our amplitude of the input voltage is not large enough. For example, here this is our input voltage, this is our V on, the voltage drop across the diode when it conducts, and now conduction is possible only if Vi exceeds V on. So that means up to this point no conduction is possible, Vo is 0, and then the diode starts conducting, and then Vo is equal to Vi minus V on. So clearly this Vo is not what we would like, and therefore we need an improved circuit. Here is an op-amp circuit, and it works as a half-wave precision rectifier, and we will see that the voltage drop V on of the diode does not appear in the Vo versus Vi relationship for this circuit. We will figure out why. So let us take two cases. One, D is conducting, and when the diode is conducting, we will replace that with a battery, say 0.7 volts for a silicon diode, and in that case this feedback loop is closed. The op-amp operates in the linear region, and the circuit looks very much like the op-amp buffer circuit that we have seen, except for this voltage drop there. Now since the input current I minus is 0, this current, IR is equal to ID, so the current path is like that. And what is V plus minus V minus then? It is equal to VO1 divided by AV, the voltage gain of the op-amp, which is a large number, something like 100,000 for the 741 op-amp. What is VO1? Remember, the diode is conducting, so therefore VO1 is VO plus this diode voltage drop, which is say 0.7 volts. Therefore V plus minus V minus is VO plus 0.7 divided by AV. Now since AV is such a large number, this quantity is nearly 0 volts, and therefore V plus and V minus are nearly equal. What is VO now? VO is the same as V minus, and therefore VO is nearly equal to V plus, which is the same as Vi. So when the diode is conducting, we have Vo equal to Vi. Okay, now let us figure out when this situation happens. That is, when does D conduct? This situation arises only if ID is greater than 0, because that is the only way the diode can conduct. It cannot conduct in the reverse direction. And therefore since ID and IR are equal, that is our current path, IR is also positive, and therefore VO, which is R times IR, is positive. So this situation, namely diode conducting, happens if VO is positive, and since VO and VI are equal, that means VI is also positive. So in short, if VI is positive, VO is equal to VI. That's a straight line passing through the origin with a slope of 1. And the most important point to be noted is that V on, the diode drop, does not appear in the graph. What happened to V on? It got divided by this very large voltage gain of the op amp. Let us now consider the second case, that is D not conducting. So we replace D with an open circuit. And now there is no possibility of any current here because there is no current going in or out of the op amp. So therefore VO is equal to 0. What about VO1, this op amp output? Since the op amp is now in the open loop configuration, there is no feedback path because this loop is broken here. A very small Vi is enough to drive it to saturation. Note that V minus is the same as VO, which is 0 volts. So therefore all it requires now to drive the op amp into saturation is a small value of Vi. And that Vi has to be negative because we have already considered the other case when Vi was positive, the last slide. And that means V plus is negative, V minus is 0. So therefore the op amp is going to get driven to minus Vsat. And that is what VO versus Vi would look like in this case. VO is simply 0 when Vi is negative. This plot summarizes the operation of the half-wave precision rectifier. When Vi is positive, VO is equal to Vi. The diode conducts. When Vi is negative, VO is 0 and the diode does not conduct. This circuit, this box here, is called the super diode. Why is it called super diode? Because it behaves like an ideal diode with V on equal to 0 volts. And it is represented by this symbol sometimes. When the diode conducts, the op amp operates in the linear region and we have V plus nearly equal to V minus. Just summarizing the important points that we have already looked at. When the diode is off, the op amp operates in the saturation region. V minus is 0, the same as VO, which is 0 when the diode does not conduct. V plus is Vi and therefore VO1 is equal to minus Vsat. One question that arises is, where does IR come from in this figure? Does it come from Vi? The answer is no. It actually comes from the op amp. So it is supplied by the op amp power supply. That's something we should remember. Let us now look at an application of the super diode or the half-wave precision rectifier, and that is AM demodulation. AM signals are amplitude modulated signals, and let us see what those are first. There are three components involved in amplitude modulation. One is the carrier wave C of t, which is a sine 2 pi fc times t, and fc is called the carrier frequency. Now this is a relatively high frequency, and here is an example of C of t. Then there is the signal itself, for example an audio signal, and it could be of the form small m of t equal to capital M sine 2 pi fm t plus some phase angle. Now this fm is a frequency which is much smaller than the carrier frequency, and here is an example of small m of t. clearly this frequency is much smaller than this frequency. And in real life, of course, this modulating signal is not generally just a simple single sinusoid. It could be much more complex. But all the frequency components of the modulating signal are much lower than the carrier frequency. And from the carrier wave and the signal, we derive the AM or amplitude modulated wave, y of t equal to 1 plus m of t times c of t. And we will assume that this capital M is less than 1. So here are the waveforms. We have A equal to 1, the amplitude of the carrier, M equal to 0.3, this number, Fc is 200 kilohertz, the frequency of the carrier, Fm is 10 kilohertz, the frequency of the signal, and clearly this Fm is much smaller than Fc. This is our y of t, and what do we notice? We notice that the frequency is the same as the carrier signal, but its amplitude goes on changing, and that dashed line shows the amplitude of this y of t, and that is of course because we have this 1 plus m of t here as a prefactor in y of t. Now this is called the envelope because if we see carefully, this signal waveform is enveloping the carrier in y of t, and the goal of AM demodulation is to detect this envelope, which is the same as our signal. Now these numbers are representative. In real life, if you are talking about audio signals, then the numbers can be somewhat different. For example, with the Vivid Bharati channel, the carrier frequency is 1188 kilohertz, and FM is the audio frequency, which can range say from a few hertz to like 12 or 15 kilohertz. Here is a circuit using the super diode, which can be used for demodulation of AM signals. It's essentially a peak detector, and we have looked at this circuit earlier when we were talking about diodes. The only difference is that it has a super diode here with V on equal to 0 volts. So therefore it can work with small input voltages. For example, here the input voltage is only 150 millivolts or less. The input voltage is shown by the light blue waveform, that is our amplitude modulated signal, and the purpose of this circuit is to detect this envelope, that is our signal. When Vi is larger than V1, the capacitor gets charged, otherwise it discharges through this resistor. So the charging happens through the super diode and discharging through the resistor. And here is an expanded view of these waveforms, which shows this charging and discharging process more clearly. So here we have charging, then discharging, then charging, then discharging, and so on. And this V1 is almost what we want, but not quite, because it has got this little ripple riding on it. So it is not this envelope that we are seeking, but the envelope with some ripple voltage on top of it. And we of course want to remove that ripple voltage, and that is done with this filter here, which we have not shown in detail. So the final output is the output of this filter, which is indicated here by VO. Now the time constant RC here has to be very carefully selected, and let us demonstrate that with this circuit file. Here are some simulation results. with R equal to 33K and C equal to 20 nanofarads and carrier frequency of 20 kilohertz and the signal frequency of 1 kilohertz, we get this result. And here the output is what we would like. This is the envelope which is detected as the output voltage, and it has got a small ripple riding on it, which we can filter out. Alright, now if we increase the capacitance from 20 nano to 100 nano, then this is what we get. And this definitely has a problem because we are missing out on some peaks here. And definitely this output voltage is not a faithful reproduction of the signal voltage. What if we make the capacitance too small? For example, this plot corresponds to C equal to 5 nano. And in this case, the output does follow the envelope, but then the ripple voltage is a little too large, which again is not desirable. So that indicates that this RC time constant must be carefully selected, and that would depend on all of these parameters. Here are some more circuits in which an op-amp is used to eliminate the voltage drop across the diode when it conducts, that is V on. So for these circuits, we will answer these following questions in the subsequent slides. Question 1. What is the function provided by each of these circuits? We will analyze these circuits and look at the functionality that each circuit provides. Second, we will verify that functionality with simulation. In addition, of course, you are encouraged to go to your electronics lab, hook up these circuits and look at its function as well. Although there are 4 circuits here, essentially we need to look at 2 different circuits, this one and this one, and the other circuits operate in a very similar manner. For example, this circuit here is derived from the upper circuit simply by changing the direction of the diode. Similarly, this circuit here is derived from this circuit by simply changing the direction of the diode. Here is our first circuit. We have an op-amp here with the non-inverting input connected to a reference voltage VR. This reference voltage could be adjusted using a pot, which we have not shown in this figure. So as far as we are concerned, this VR is simply a constant. Alright, this is our input voltage, and we will take an example of a sinusoidal voltage applied as Vi, and this is the output voltage. Let us see what the circuit is doing. Let us first consider the case where the diode D is conducting, and when D conducts, the feedback path is closed, this path here, and we can expect V minus to be then equal to V plus, these 2 voltages, and V plus of course is equal to VR, so therefore V minus is equal to VR. V minus is in fact the same as VO, so therefore VO is equal to VR. So that is the situation when the diode D conducts. Now when does that happen? To see that, let us write the KCL equation at this node. We have 3 currents here. One is ID, so that ID is equal to this current plus this current. This current is simply VO by RL, and VO is the same as VR as we saw. So therefore this current is VR divided by RL. What about this current? This current must be the same as this current here, because the input current for the op-amp is 0, and therefore we have VR minus Vi divided by R. So that is our KCL equation. Now the diode current ID can only be positive because the diode cannot conduct in the reverse direction. So therefore this quantity must be positive, and what that means is VR times 1 over RL plus 1 over R must be greater than VI by R. In other words, VI must be less than VR times R plus RL divided by RL. This factor is always greater than 1, and we will define this entire quantity as VI1. When Vi is less than Vi1, the diode conducts, and we have Vo equal to Vr, which is a constant, and that happens irrespective of Vi, as long as Vi is less than Vi1. So that is one situation that we have. And in the other case, that is when Vi is greater than Vi1, the diode does not conduct, and what do we have then? Then this current is 0, and we have Vi dividing between R and RL. So then Vo is given simply by voltage division. Vo is then RL divided by R plus RL times Vi, like that. And here is the plot of Vo versus Vi. This axis is Vo, this axis is Vi, and this value here is Vi1. When Vi is less than Vi1, that means this region, Vo is constant and equal to Vr, like that. Otherwise, Vo is given by RL by R plus RL times Vi, which is a straight line passing through the origin, this line, with a slope equal to RL divided by R plus RL. So this circuit is essentially a clipper circuit. Alright, let us now take a special case in which RL is much larger than R. When that happens, this factor becomes equal to 1, and our Vi1, this boundary here, becomes equal to Vr, and the slope here becomes equal to 1. To summarize, we have looked at the super diode, a combination of a diode and an op amp, which behaves like an ideal diode with turn on voltage equal to 0. We then looked at an interesting application of the super diode, namely AM demodulation. After that, we have started looking at precision clipping and clamping circuits. We will continue with this discussion in the next class. Until then, goodbye.